Okay, we're going to talk about magnetic induction. Now, this chapter is actually last on the homework list, but we're going to talk about it today anyway. It's the last on the homework list because it's not DC. What's the name of this class? DC electricity. Magnetic induction is AC. Different subject. But where do you go after we finish with these classes? You go to the second semester, which is all AC. Very good. Okay. So, we're going to talk about the factors that determine the amount and polarity of induced voltage. We're going to talk about Lenz's law. We're going to talk about RL time constants. Very important idea, RL time constants. Where's my slide mover on this thing? I've lost it. All right. Anytime you have a wire, this little center drawing here is the center of the wire. And because that's the center of the wire, something happens around the outside. Now this, again, we're talking about AC. Why not DC? Because DC doesn't induce. Because AC is constantly rising and falling. You've seen a sine wave, right? That's how electricity is produced. It's produced in a sine wave. The voltage, the instantaneous voltage is rising, then falling, and then going the opposite polarity, then rising in positive polarity, falling back to zero, going down to the bottom. We'll talk about that maybe today. Go away. And because of that, what do we have here? What is this thing? No, it's an electromagnet, I hope. But I think it's showing a permanent magnet. That's probably true. Now, if you take a permanent magnet, it's got flux lines that are happening that you can't see, right? It's kind of like electricity. You can't see it, but it's happening anyway, right? And you take that one wire and you wave it up and down between those flux lines. What's going to happen? This thing's going to create some voltage. It's inducing some voltage. Is that the same one? Okay, so there we go. It's making some voltage. We shake it one way, it goes one way. We shake it the other way, it goes the other way. And then we need a rule to find out where the polarity is happening. Whose law is this? It's the left-hand generator rule. The generator rule. The generator rule is one rule, right? And so the current is indicated by one of your fingers. Notice this thing right here. And this is the field. And that's the motion. If you're taking a single wire and moving it through the magnetic field, this is what would happen. And the polarity is the tip of that finger right there. Let's see if I can move that up. Okay. So if we have a coil and we shove a magnet back and forth in it, there's a little flashlight where it's got a really strong really strong magnet in it, a neodymium magnet, and you shake the magnet and you make it jump back and forth inside the coil of wire, and it creates and stores a small amount of electricity. There are little flashlights where you can get those things that do that. And then the kind of the other way around is if we spin the wire around inside two different magnetic fields, which is kind of how electricity is generated. And if we want more power, and we always do, we add more what? Wires. So we wind those wires around and around. And what do we call that? Windings. Windings. We have windings that are going around and around here, right? Okay. Okay. Lenz's law, an induced voltage or current opposes the motion that caused it. Now, what if a different current is creating that induced voltage? They're going to be opposite in polarity. Inductors always oppose a change of current. Sounds like that thing about motion. If a body is in motion, it wants to stay in motion. A body at rest wants to stay at rest. Same kind of idea, okay? Only slightly different, of course. Okay, inductance is determined by the physical construction of the coil. Notice this winding is wound in the same way. No, these are wound in opposite directions, aren't they? No, these are wound in the same way. But you notice that you could, okay, take a look at this one on the left, and this one's, the only difference between this one and this one is that it has more windings. But couldn't we wind around the other way? Everybody see that? What would happen if we wound it the other way? What would change? Polarity, exactly correct. That's exactly correct. Beautiful. Okay. We would reverse polarity, exactly. Okay. Now we need to talk about RL time constants. Now what is R and what is L? Inductance in henries and resistance in ohms. Now any wire at all has resistance, right? Now what are we talking about here? Are we just talking about anything in the world? We're talking about that winding, right? We're going to take that winding and we're going to do something with it to create some voltage, right? And it's got inductance. The more windings, the more inductance. Okay, the more windings, the more inductance. Okay, and the time constant is how fast that instantaneous voltage starts coming up. Okay. Current flows, magnetic field is created around the conductor. When a conductor is cut by magnetic fields, which is the opposite idea, right? A voltage induced is in the conductor. And this is how transformers work. You have one winding and current is flowing through it and it's inducing current into the other winding. Now let's go back to our little drawing here where I kind of wrote on it. And if we had this winding inside this winding, literally, and let's say that a piece of iron is in between, let's say this core right here is an iron bar, and we take this winding and we wind this on here, and then we wind this winding over here on it. No, I didn't want to do that. Okay. So if we put this winding over the top of this winding, now they're wound the same way, right? And we run current through this one with fewer loops, and this other one with more loops is over the top of it. What's going to happen? This current is going to induce current into this other winding. And is it going to have the same polarity as the current in this one? It's going to have the opposite polarity. Because what does Lenz's law say? The current that's induced is opposite in polarity to the current that induces it. Well, actually, we haven't found that out yet, have we? Okay, well, that's all right. We're going to find that out yet. Okay. And I still don't have my slide mover. Okay. Now, time constants describes the time necessary for current in an inductor to reach its full Ohm's law value. What does that mean? It's full voltage. Okay. So we are talking about the two coils where we're inducing current in one and it induces current in the other. Okay. I want to give you a more realistic view of this RL time constant. You start a motor up and you hear it go, right? An electric motor, and you hear it spinning up, right? Do you realize that there's a lot of current inrush into that motor at first? Because at first, the magnetic field that's rising and falling presents no inductance to the current flow. The only thing that's resisting current flow is the pure DC resistance of that coil of wire. So when a motor first starts up, it draws a lot of current. The only thing preventing it from drawing current is the pure resistance of the wire, which is usually very little. So the current flow immediately is very high. But as that magnetic field builds up, it builds up inductance by building and collapsing that magnetic field, which takes energy, and it presents a kind of resistance. And that total of pure DC resistance and that inductive reactance, we call it, is called impedance. And that's an idea we're going to come to sometime soon, but not today. Okay, believe it or not, that's everything on this chapter, I think, almost. Let's see. When current flows, a magnetic field is created around the conductor. Conductor is cut by magnetic field. The opposite happens. It creates a current. Let's see. Polarity in the induced voltage is determined by the polarity of the magnetic field or the current that's inducing it. And let's see. What affects the amount of induced voltage? The number of turns of wire. The number of turns. More turns? Okay. The strength of magnetic field and the speed of the magnetic flux cutting action. In other words, if you're spinning an alternator, the speed it's being spun at affects the voltage. Okay. All right.